Here we will look at another advanced example of an indeterminate form. And in this case, we're looking at the indeterminate form of infinity minus infinity. So let's think about the case where you're subtracting two fractions and taking a limit as x goes to a. The first fraction is going to infinity, the second fraction is going to infinity. But this limit could turn out to be anything, because it depends on the relative rates at which the first expression is racing to infinity versus the second expression racing to infinity. You could get 0. You could get any constant. You could get infinity. You could get minus infinity. Hence, infinity minus infinity being an indeterminate form. It's not a defined thing mathematically. In this case, we can try rewriting this expression with a common denominator. So take the first expression and multiply top and bottom by z of x, the denominator of the other. And do the same for the second expression. Multiply top and bottom by g of x, the denominator of the other expression. When we do that, we get a common denominator of z of x times g of x. And in the numerator, we get z times f minus y times g. And we do this because this new form may yield a 0 over 0 or infinity over infinity indeterminate form, in which case we can use L'Hopital's rule. Let's see this in an example. The limit as x goes to 0 from the right of 1 over x minus cosecant of x, which we rewrite as the limit as x goes to 0 from the right of 1 over x, and recall that cosecant of x by definition is 1 over sine of x. Looking at these terms, if x is getting really small but staying positive, its reciprocal is blowing up. So that first term is going to infinity. The same is happening with 1 over sine of x. If we think about our graph of sine of x, as x approaches 0 from the right, sine of x is approaching 0. So the same phenomenon is happening with the 1 over sine of x term. So we have an infinity minus infinity indeterminate form. But we use the approach we summarized on the previous slide, and we rewrite this expression, getting a common denominator. So that 1 over x term, let's multiply by sine x over sine x. And the 1 over sine of x term, we multiply by x over x, which gives us a common denominator of x times sine of x. In the numerator, we have sine of x minus x. And let's see if that helps us at all. Well, if we try to directly evaluate, in the numerator we see, as x goes to 0 from the right, sine of x goes to 0, and also the x goes to 0. So that numerator is approaching 0. The same is true of the denominator. X is approaching 0, sine of x is approaching 0, so their product is approaching 0. And this gives us an indeterminate form that we can work with using L'Hopital's rule. So using L'Hopital's rule, we have the limit as x goes to 0 from the right of derivative of the numerator over the derivative of the denominator. The derivative of sine of x is cosine of x, and the derivative of negative x is negative 1. In the denominator, we need product rule. So first, x times the derivative of the second, derivative of sine of x is cosine of x. Plus the second, sine of x times the derivative of the first. Derivative of x is 1. And now let's see if we've gotten anywhere. Well, think about the graph of cosine of x. We know cosine of x looks like this. And we know as x approaches 0 from the right, cosine of x is approaching 1. So the numerator is approaching 1 minus 1, or 0. How about the denominator? Well, we just argued that as x goes to 0 from the right, cosine of x is going to 1. This x is going to 0. So this term is going to 0. We also know that sine of x, as we just argued, is approaching 0. So the denominator is also going to 0, which means this again gives us a 0 over 0 indeterminate form, which allows us to again apply L'Hopital's rule. So a second application of L'Hopital's rule, we need the derivative of the numerator over the derivative of the denominator. The derivative of cosine of x is minus sine of x, and the derivative of negative 1 is 0. So our numerator is negative sine x. In the denominator, we again need product rule for the first term. So the first, x, times the derivative of the second, the derivative of cosine of x, is minus sine of x, plus the second, cosine of x, times the derivative of the first, derivative of x is 1. And then we have plus the derivative of sine of x, which is cosine of x. Or the limit as x goes to 0 from the right of minus sine of x over minus x times sine of x plus 2 times cosine of x. And let's see where this gets us. As x goes to 0 from the right, negative sine of x is approaching 0. When we look in the denominator, as x goes to 0 from the right, x is going to 0. Sine of x is also going to 0. So this term is approaching 0. But the cosine of x term, as we had argued previously, as x goes to 0 from the right, is approaching 1. So this limit, applying the limit laws, the limit of the quotient is the quotient of the limits, and then in the denominator, the limit of the sum is the sum of the limits. We have a limit of 0 over, notice we have a 2 here, 2 times 1 is 2, which is 0. So we see that in this case we had to apply not only this approach of getting a common denominator, but 2 iterations of L'Hopital's rule. You can have examples where you have many iterations of L'Hopital's rule, and that will often work.